All right, this video is going to be a very quick review about parametric and vector formulas. The good news about these is that they are rarely asked in any way that's unusual or exotic. They're very straightforward kinds of things that you do with this for the vast majority of the relevant problems. The bad news is you do need to actually know the relevant formulas. So I'll just remind you that parametric equations are a way of understanding a curve or motion where instead of directly relating x and y to each other, we relate them to a third variable called a parameter, and that's often called t. And it's helpful to think of this as representing time. So maybe I have some particle moving around, and here's where it is at t equals 0. So we can think there's an x coordinate that tells us where we are at that time, and a y coordinate. And then maybe later on at t equals 1, there's an x coordinate for 1 and a y coordinate for 1. And then maybe later on, here it is at time 3. I'm skipping some numbers. Maybe here it is at time 5. And we can imagine that this is part of a curve where it's moving around, right? Y is not a function of x, but we do have some curve that makes sense. And presumably there will be one function that's just keeping track of where do all these x coordinates come from, presumably in a predictable way. And then a different function that's keeping track of the y coordinates, presumably in a predictable way. So that's the idea. There will be one function. Let me match the colors. One function is x of t, just what is our x coordinate? What is our horizontal position as a function of time? And the other is y of t, what is our vertical position as a function of time? Now, occasionally, actually more than occasionally, roughly half the time in terms of AP problems, this is presented in vector form. It's exactly the same information. It's just a question of how we present it. So here would be an example where we have parametric equations, plural. Here's the equation that explains x. Here's the equation that explains y. When we're thinking of it from a vector point of view, we can think, oh, I have one vector. Here is my vector that explains position as a function of time, and it has an x coordinate and a y coordinate. One might call this an x component and a y component. It's the same information. It's really just a question of, am I thinking about x and y separately, or am I tying them together into a single vector? In terms of problems that you might see, sometimes you'll see problems where you're given the x and y functions or the vectors. Sometimes you're given the derivatives, the first derivatives, and you might need to work backwards to figure out the position. So we're going to quickly run through the kinds of things you need to figure out. I'm not even going to do any examples, but that will be part of your assignment. So if we want to find rate of motion, x prime of t basically just explains from a purely horizontal point of view, how fast are we moving in which direction? Maybe we're moving up and down, but if we're just paying attention to the horizontal motion, this measures it. Y prime of t does something analogous for the vertical rate of change. And then obviously we could just put these together into a vector that has these two individual derivatives as its components. Acceleration, we just go one derivative beyond that. If we were watching this thing move, it might make sense. We might be able to see when is it accelerating, when is it decelerating. Sometimes that's reflected in a change of direction rather than a change in speed. So the acceleration vector is something that's hard to observe in certain cases, but relatively easy to compute. Okay, what about slope of a tangent line? Right? Maybe we're moving around and there's some point here, and we want to know how steep is the graph right there. Figuring out the slope of that tangent line is equivalent to figuring out, well, more or less equivalent to figure out the direction of movement at this very point of time, roughly speaking, in which direction is the particle moving. And this has a really nice formula, right? Slope of a tangent line, as always, is dy dx. And it turns out that if we cheat a little bit about this, we can say, oh, you know what, like just the dt's cancel. Do the derivative of y with respect to your parameter, do the derivative of x with respect to your parameter, and take the ratio. It's just the ratio of vertical rate of change to horizontal rate of change. It's as though these differential dt's cancel. We also want to know speed. So speed doesn't have a direction, just in whichever direction we're moving, how fast are we moving in that direction? And there is something about this that should remind us of Pythagorean theorem. This is essentially computing the length of the velocity vector. So if we imagine we have some velocity vector like so, here's our velocity vector. Kind of the idea is here is x prime, here is y prime. Speed is essentially figuring out how long is that thing, kind of as a Pythagorean theorem applied to rates of change. Total distance traveled, which is the same as arc length, right? If I'm moving along some curve and I'm starting here at t equals a and I'm ending here at t equals b, well, how far did the particle actually go? That's essentially measuring how long is that curve. And that's just a definite integral of speed. Right? Speed is the rate at which that distance is changing. So the total distance is the definite integral of speed. So this can be cumbersome to compute depending upon how weird your formulas are. Even typing this into your calculator requires some care. But the formula is just its formula, right? You're rarely going to be asked hard things about this besides just what is it? Now, what about change in position, right? Change in position is displacement, right? Displacement, the displacement vector would just be like, I don't care about the path you took. Just how much did you change? And this is where we remember that change is computed by finding the definite integral of a rate of change. So change in x is just the definite integral from a to b of the rate at which x is changing. The change in y is the definite integral of the rate at which y is changing. The displacement vector is just the vector that puts these things together. So certainly a problem you might see is, we're given that our velocity vector is sine t squared plus 4. And we're told that at time equals 0, the particle is at 3 comma 5, and we want to know where is it at t equals 7. So to find our new x coordinate, the x coordinate times 7 would be the x coordinate we started with at time 0 plus the definite integral of the rate at which x is changing. The y coordinate is the same thing with y's. This principle comes up in so many different forms. It's not unique to parametric. It's not even unique to motion. If something has changed, then the amount that it has changed is the definite integral of the rate of change. This is one of the most important concepts in the entire curriculum of calculus. They ask it a lot on the AP exam in many different forms. Okay, and then the very last one. Concavity of polar curves is mentioned explicitly in the curriculum guide. However, from what I can tell, it shows up very seldom, right? This is the kind of thing, maybe one multiple choice question, maybe one part of one free response question. But I will just remind you, if we want to find the concavity of the curve, right? So concavity is always measured from the point of view of x and y coordinates, just like slope. First of all, I will tell you this is not y double prime of t over x double prime of t. It would be great if that's how it worked. It's far more complicated. Here's how we actually do it. It's the derivative with respect to the parameter of slope over the derivative with respect to the parameter of x, right? I should really just write that bottom as dx dt. And obviously slope, we already know how to find. So this is not a straightforward computation at all. But it is doable. So here, I will do one example of this. So let's suppose we have that x of t is 4t squared, y of t is 3 minus t, and I want to find the value of this second derivative at t equals 4. So first, let's just find the slope. So the slope is y prime of t over x prime of t. That would be -1 over 8t. So our second derivative of y with respect to x, the thing that measures the concavity, as a general formula, would be the derivative of this speed function over what we've already figured out as the derivative of x. Everything now is in terms of the variable t, because I've expressed slope, not speed, slope. I've expressed slope in terms of t only. So I'll just note what I actually have here is -1/8 t to the -1. So the derivative up top would be 1/8 t to the -2. dx dt as before is 8t. And this appears to simplify to 1 over 64 t to the third. So if we were to evaluate this at t equals 4, we would have 1 over 64 times 4 to the third, which is 1 over 64 times 64. 64 times 64 is, well, what is that? Well, I don't have a calculator with me. This is 2 to the 6th times 2 to the 12th. So it's actually 4096. Right. Some set powers of 2 I just have memorized. Don't think that I actually did that arithmetic in my head. And again, don't worry too much about the evaluation here. Right? So this is doable, especially if your slope formula is not super hard. Right? We have managed to avoid quotient rule in here. Right? It's straightforward, it's just tedious. And you need to know this formula because it's not particularly intuitive. Right? There is a reason for it that's not crazy, but it's not what you would guess. Okay, that's enough for this video.